We can continue with the third exercise which I prepared, which will be extension of the first one when we add the encryption. Because what we created till now, that we have the code inside the external memory, which is then read by the STM32 and then executed. But all this content, the link between the memory and even memory itself, if somebody unsoldered the memory or connect there the probes, he can observe all the content of our application. So he can basically steal it if he wants. What we will do, we have one periphery inside called the MCE, which allow to encrypt and decrypt all the accesses which are memory mapped and automatically do the decryption in our case. And then the core itself will see the decrypted data. There is no overload for the code. He will not see this data. He will only see the decrypted data. So this is advantage for us. But we need to configure the peripheries. So what we will create, we need to modify our bootloader to start using the MCE unit. And also we need to configure the external loader to not only use the MCE for the decryption, but also to use it for the encryption. And our code will be like before, the standard toggling from the exercise 1. So we will not touch the application part. In this part we only will work with the bootloader and with the external loader. We can switch or open back the CubeMX from the exercise 1. And what we need to do is to select the MCE. If you search for the MCE, you will discover that we have 3. So which one you want to choose? For this, I have the slide to show you, where each MCE belongs to the one periphery physically. So in our case we're using XSPI1, so to this belongs to MC1, to the XSPI2 belong MC2, and for the FMC periphery for the parallel external memories belongs the MC3. So in our case we want to activate the MC1. So we will select the MC1. We will select MC1 for the bootloader and for the external memory, and we will activate the MC1. There is no configuration in this. We need to configure the MC by ourselves inside the code. Luckily, the MC configuration for the bootloader and for the external memory will be quite similar. I think we change only one item from the initialization structure, which is quite nice. However, if we now generate the code and configure the MC, it will not work how we expected. The reading will be fine, so the bootloader will be fine, but we will have the issues with the external memory loader, and mainly during the programming, and I will try to explain you why, and it have to something to do with the external memory manager, how he working with the write. The main issue what we want to have is that with the MCE we need that the core will access the directly memory mapped area which is covered by the MCE and also with the XSPI. So XSPI needs to be in the memory map mode, so it will be visible on the address 90 million, and he needs to write over this, otherwise the MCE will not work. But what we get, it's that the external loader by default using the external memory manager library, and it's not using the memory map mode but using the direct mode, so it's working as a standard SPI, so you're writing into the register and he writing into the memory, which is not what we want. By default it looks like that the external memory loader will call write, the write will call the write wrapper, and the write will call external memory write, and then depends on the library which we selected. But we have the solution. We can override this step, and instead of this memory write, we can use the write in memory map mode, so which will effectively help us to use the MCE unit. So we will override it, and then it will allow us to use the MCE. It can look that it will then work as we expected, but unfortunately there is something even more tricky. The one part is the MCE, which for the write, and because for the encryption you need to have the block of the data, so the MCE itself requires 16-byte burst of the data. And the second issue is the external memory itself, because for the one write command you need to have the consecutive write of this complete page, which we have 256 bytes. So in our case, if we only overwrite this write in the memory map mode, so he will call the driver to write in the memory map code, and how he is writing in the memory map, he using the simple copy of the memory. Unfortunately, if the core is copying into the memory, he cannot guarantee that the write will be consecutive, so the write can be interrupted. Then he continue with the write and then to create the next write, but unfortunately our external memory will not accept it. He will accept only the first one, and it's possible that if the write is even shorter, then the MC unit will also not accept it, so he will not write into the external memory and nothing at all. As a solution, we can use the only unit which will create the perfectly continuous write, and which is the DMA. So we will override this mem copy, and we will use our mem copy, which we will define, and the write then will be consecutive and memory will be happy. So all the data which we will write will end up inside the memory. Of course, as an additional feature, to be sure that during this write the core will not accidentally read or write into the memory, we can use the last unit, which is the MPU, to be sure that only the DMA will access the external memory. So we are 100% sure that the core cannot bother us in case that there will be mistake in the software. The MC is then enabled. I will cross-check that my MPU is still configured correctly, so check the boot, and in the boot you should have the second region for the 90 million. We can allow access for the privileged read and also for the non-privileged read. In case that you have the free RTOS, it will be important. But you can stay even only with the privilege, it's no issue, and you should have the cacheable and the bufferable, and of course we need to have the instruction access because we are running code from the external memory. So only cross-check that this is there, that it's not disappear or we didn't forget to set it. But I told you that we need to use the DMA. So we will go to the DMA. We have here two DMAs, and I think we can use the HP DMA because it's on the same bus as MCE. I can use any channel which I want. I will use channel 0. We will not use it in the bootloader, but unfortunately we cannot generate the configuration inside the external loader, so we use it as a template and we not use it inside the bootloader. I will here switch to the channel 0. A request will stay software. Only what I want is here, the source and the destination modes. Definitely I want to increase the address after transfer for the source and also for the destination, because it will be like the mem copy, so all the addresses needs to increase. I will transfer by the bytes. And because of the MCE, which require burst of the 16 bytes, I need here put 16 for the source and also for the destination. And this is all configuration which we need for the DMA. So here enable the increments and set here the burst to 16. If you not select burst of the 16, it will not work. This is all for this configuration. For the clocks, there is nothing to change in the project manager. I want here to do one change in the advanced settings. We don't need to use the DMA, so I can here select to not generate the function call. So the init will be there, but it will be not called. So effectively in the bootloader, it will be not compiled. Which is perfect for us because we save the space. and click generate. My code is now generated. We can switch to the Cube IDE. Here I can open the Cube IDE. In case that they are not refreshed, you can press F5 and it will refresh the projects. And we will go to the bootloader and to the main.c. And first, because the bootloader will be the simpler one, we set the bootloader for the decryption of the content which we have on the external memory. So first, what I need to do, if I will start decrypting, will be good to have the key. So I will create my key and I put it here into the private variables. It's only testing key. It's definitely nothing robust. So my key is 123478 and it's 128-bit key. I assume that in your normal application you will store, for example, your key different for each device, for example, at the end of the internal flash, or you will have more sophisticated key. This is only for the testing purposes, that we know what the key is and where it will go, so we can recognize the numbers. And the second part is to add the MCE configuration. And I will put it here before we boot our application. I can put here the brackets. And we will need two structures for the MCE. One will be for the configuration and second will be for the region. For the configuration, I will show you the slide, what configurations are available, because not all the MCEs are the same, but because we have XSPI1, we are stuck with the AES configuration, so I will show you the slide for this. For the MC unit, we can have up to 4 regions, and you can decide inside the memory where the regions will be and if they will be encrypted or not. You are not forced to encrypt the complete memory. You can only encrypt the specific parts of the memory, for example, the one with the code, but I assume, for example, the pictures, if you have only the background for your screen, you don't want to encrypt because it will only increase the time which you need for the decryption. So you can choose which one you want to encrypt and what will be the accesses into the regions, because some can be privileged, some can be unprivileged, some can be with the write access, some only with the read access. It's really up to you. For the MCE, we have the MCE1, which have the AES encryption and decryption engine. And you can set the two modes. One is the block mode and second one is the stream mode. The block mode, it's a little slower than the stream mode, and stream mode is quite efficient for the coding, the decrypting the code, because how he works. This I will explain you in a few slides. The other MCEs are not using the AES, they're using the Neocon encryption and decryption engine, and they have only the block mode. So for this, if you want to decide which one you use for the code, I would recommend for the code data to use the MC1 with the stream mode. And in case that you have MC2, then this can be used beneficially for the RAMs, because with this, the read and write will be always inside the block mode. The difference between stream mode and the block mode. If the SPI asks for the read, in stream mode, the memory starts to reading the data from your memory, so the XSPI is reading, but the MCE in the same time starts to decode, because he is not decoding directly the data, but he is decoding the address and something called the initialization vector. And when the reading is done, basically he do only XOR and immediately give you data back. So in case that your memory have some latency, so you can get the data and in the same moment you will do the XOR, so there will be minimal latency during the reading. So for the code execution it's very effective, because you will not see the decoding time or the decryption time of the MCE at all. In the block mode is the situation opposite. You will do the read. You are reading the data from the external memory, and when you get there, the MCE then start decoding this data, which take also some time, and after that he will give you the data. So the block mode will be always slower than the stream mode. Back to our configuration. So first part, I will configure the key into the AES. I have this initialization vector, which are this nonce and the version. This is my initialization vector and also the key. So this will be always part of the decryption plus my address, and I will activate the configuration for the context 1. I think on this MCE I can have multiple context with the multiple keys. So I think I can have up to 2. If I go back, yeah, I can have 2 contexts, and I think in each context I can have different key, which is good, because if I have multiple regions I can have even the different keys for them. And I can enable the AES context. This is what I need to do. The second part, it's the configuration of the region. So I'm telling that the region will use the context 1. I'm telling him what the region will be, size of the region. So I'm putting the 90 million, and I simply putting then the end of the memory. I don't think it's my 32 megabyte. I'm telling him that I want this stream mode, which is very important. And I'm telling him that I want this configuration only to be read only. So he will not allow me to write anything into the memory, because I'm in the bootloader. I don't want to write there. And you can select if the access into this region will be privileged or unprivileged. Because I'm don't having any RTOS, I'm always privileged. So here it's no issue. And of course, at the end, I need to set the configuration into the structure. I'm missing H. So I will, this pconfig, I put as a region 1 into the HL structure. I will set the region context, so they are linked now. And also I will enable my region. And that's all. After that, when I enable this and when the bootloader switch into the memory map mode, all code will be decoded, but of course it will not work now because inside the external memory I don't have yet the encrypted image, so I need now work on my external loader. Last part in the bootloader, we can check that we can build the project. So right click and set build. Also check if inside the drivers and the HAL drivers you should have the MCE and the GPDMA, the DMA here. In case that is missing, try to generate the code from the CubeMX again and check that you enabled the DMA and also the MCE. And we can now move to the external loader, which will be a little bit more complicated, but not so much. Inside the external loader, we can again go into the core source, and we will work mainly in the external with the external loader in it. So we can open this file. I will close the rest of them. And what we need to do, it's we want to change this writing sequence, which is here in the memory wrapper, and we want to change this memory write. So we can take it because it's weak. We don't need to rewrite it here. We can just take it. It's inside memory underscore wrapper.c, and we copying this memory write and copy the complete function. And we put it inside the external memory loader underscore init, and I will put it here on the top. Oh, sorry, not here. This is for the private variable into the section 0. It will be little bit better. And we need to change here only two things. One is the address, because before it was used indirect addressing, so he was masking the address, because on the memory the address starts from the 0 and not from the 90 million. But in our case we will use the memory map mode, so we want the full address, so delete this masking, so the full address will be propagated into the function. And the second part, it's we want to change this function to not use the memory write, but we can use the control space, and we can use the memory write, external memory write in memory map mode. So we will select it, we need to delete this bracket, and we don't need to change here anything at all. But what we don't need to forget is to include the wrapper, to be sure that we can use this defined, so otherwise he will be really unhappy with it. We need to include this memory wrapper into our project. So include this, and it will allow us then compile our code. So this will take care about the writing. So now the write will be inside the memory map mode. But we still need to solve the issue with the DMA. So inside the driver, which is normally used, it's there the SFDP driver. And here, for the memory copy, it's at the end. It's used this function, which is basically the software mem copy. And we can copy it because it's again the weak. We don't need to copy it all, only the function, because we will create our own implementation of this function. And again, we will put it into our external memory loader in it. And we need here to create our own initialization function. The first thing I need to do, because I'm not sure how this source data are formatted, and it seems by my test that if they are not aligned, the DMA will not work properly and create the gaps during the writing. So I will create here the temporary buffer, which I will align to be sure that any DMA read or write will be not changed. It's called only buffer, nothing more, and the size of the buffer is the size of my maximum read, which is 256 bytes, which is 100 hexadecimal. And I will simply copy here using memcopy, and as I think first is the destination will be my buffer. The source will be this buffer, the second argument, and the size, of course, will be the data size. So I will do the simply memcopy here. So I will be now sure that all my data are here inside this memory copy. But now to the DMA. We can create the DMA configuration but ourselves, but this is the reason why we created the one configuration inside the bootloader, so we can simply take it and it will save us a lot of the time. Only what I need to do is here search for the DMA initialization, which is all this, and I will take it. We need also take the clock initialization, without it it will not work, all the initialization and the init and the configure the channel. So we can take this ones and put it here. I will delete here these commands because I don't need them. I have here the memcopy, and only thing which is missing is here the definition of this variable. So I will again return to the bootloader, and it will be on the top definition of the handle for the GPDMA, and I put it here locally. So now my DMA is configured and prepared. It was simple like that, only copying. Now I need to start the DMA. So we can use the function HL_DMA_start. The first parameter is the handle. Usually Cube IDE will whisper you the correct part. The second argument is the source buffer, which is my buffer. I can put it that he wants only the address to this buffer. Sorry, this I didn't want. _t. Just tells him that it's really only the buffer. The destination will be my destination address. Again, I can mark it as a address. And the size, of course, will be my data size. Nothing more here. But the HLDMA start is non-blocking function, so this will only start the DMA, but we are not sure where the DMA ends. So we can use another function, the HL _ DMA _ pull for transfer. Again, the same handle. The completion level, we can have two of them. One is in the half transfer and one is in the transfer complete. I will use the transfer complete, and I don't want to use the timeout function. So I will use the 8Fs, which is the maximum value, and in this case the timeout feature is disabled. In case that we will get stuck, the Q programmer will stop the program anyway. So it's no problem for us. And it should work. So we copy here the buffer, the pointer data into our aligned buffer. We will configure the DMA here. We will start the DMA, check when the DMA is finished, and then we leave this function. And it's all for this part. So we implemented now the memory map write. We implemented the configuration with the DMA. Only part what is missing was adding the MCE. I can put very similar configuration with the MCE. I will use the same key, so this part is completely the same. This part is a little bit different because now I have the read-write access. And I also have here the non-privileged access because the DMA here, it's set as a non-privileged. In case that you set here the privileged, you need also for this DMA set the privilege, otherwise the MCE will not allow the DMA to write inside this area. And what I forget, it's of course my key. So I will add the key into my project. Do not forget it, otherwise the compiler will be very unhappy with me. And I can do the one fine-tuning, which was with the memory protection unit, which I can add there. So one fine-tuning here. What I will do, I will create the variable for the memory protection unit. I will enable memory protection unit again on the address 90 million. I can now set for the full size of the XSPI1. What is important that I will allow access only for the reading, for the privileged or the unprivileged. In this case, I will not allow any instruction access because in this case I am not executing any instructions. I only programming or reading the data. I will not share the memory. It will be not cacheable and it will be not bufferable. And I will configure the MPU and of course again enable the MPU. And I also added here to disable of the caches because during this operation when we programming the external memory, I want to be sure that the data accident will be not stuck somewhere inside the cache. And this is all for this part. I can compile it. Okay, now compilation finished. You can see that he found again the Cube programmer, the Cube IDE, and we can test if this will work. I can click on the application. I can click on the debug button, we have the same configuration like before from the exercise 1. So we will again debug now together the bootloader and also the application. You see that I am now in the debug, which means that he was able to program the code. I am in the internal memory, and if I run, I see my LED blinking, so it seems that I am the external memory. Now the question is how to discover that the data are really encrypted, because it's now not visible if we can debug. I can try it through the memory window. I can put here the address 90 million. It is here, and I will use the additional one. On the beginning of the memory, where is our program, it's usually our vector table. And in the vector table, the first word, it's our stack pointer, which should point into the RAM, which 20 million is in RAM. And there are the interrupts. First interrupt is the reset. There are some fault, I think non-maskable interrupt, and some faults starting on the 90 million. So this is the traditional beginning of the memory. They're starting all from the 90 millions, and I think the table is quite large. So this is the reason why all these interrupts are starting with the same numbers, and some are reserved. If you look on the flash, which we have inside, you will see the similar picture. Only instead of the 90 millions, there will be the 8 millions. You see that the stack pointer is the same, but here all these are in the 8 millions. So this is how it should look like. And we can try to disable the MC unit to see what is there really. For this, I need to use inside the registers the MCE. We have the region 1 and MCE MC1. And I can here use this region enable and disable bit, and I can do here the step, and it should refresh the memory, and you will see what is really inside the memory, and you see that the run data are quite random, and without decoding you cannot see what is there. So we are finished. We can move to the conclusion, what we did. We were able to modify our code that we are able to encrypt and decrypt the memory. I showed you that which MCE to use, where to search which MC you want to check. We set up the MCE for the decoding inside the bootloader. And we also set up the MCE for the encoding and decoding inside the external loader. I showed you that you can override the write function to use the memory map mode. This is mainly used in case of the MCE, otherwise it makes no much sense. And I also show you that you can override this memory copy and use the DMA, which is required for the MCE, and of course for the memory which needs one long write. So now you can create your own application and be sure that it's secured. Only you need to select more complicated key and not 1, 2, 3, 4, 5, 8.